All right, everybody. Good morning. Can you hear me?
Yeah.
Yeah, good. So I have a bit of an issue with my Zoom setup because Zoom is blocking. Maybe this will help. So we got a couple of minutes to go. We are still seeing students trickle in. It's 7:58. Let's wait till 8:01 and then I'll begin. So is no, my apologies. You will see me in person in class next week. Okay. 8 o'clock. I'll wait for another minute and then we'll start. Oh, so there are some sounds outside my window. I apologize for it. I'm conducting this lecture from my home and digging up the street outside for some reason. Anyway, welcome to this to 11785 Intro to Deep Learning, also numbered 11685 and 11485. This is the fall 2023 version. By now, you must have already seen the logistics post on what's the lecture 0. We don't actually, we missed this. There will be a logistics post on Piazza, but you must have read the introductory post. And if you haven't watched the logistics lecture, please do so at once. And hopefully all of you have also already been to the course website. That's deeplearning.cs.cnu.edu. It's very easy to remember. And course objectives, logistics, quiz, homework policies, grading policies, all of these have been explained in both the logistics lecture and the course page. So please familiarize yourself with this information as soon as you possibly can. The entire semester is going to run roughly along the guidelines we have posted here. And so before you begin asking us questions, make sure you verify these, check these check these resources. Also, you should already be on Piazza. If you are not on Piazza, you should be able to sign up there. Yeah, is there a question? You must also have access to Canvas and AutoLab. And you should have, there's an AWS recitation and a Google Colab recitation. You should ideally have viewed both and made sure that you're able to access AWS and Google, because we're going to be using these pretty extensively for compute. There has actually been a note on forming study groups. So please sign up for study groups if you haven't already done so. We don't just recommend this at this point, we almost mandate it, because it's our experience that students just learn better in teams. You don't by yourself, you're far less effective than when you're working with a bunch of people who you can discuss things with. Our course philosophy is that we want to leave no student behind. So in our ideal world, every one of you would earn an A. And this doesn't mean you're going to get an easy A. Grades are very hard to get in this course. But what is amazing is that most people do get that A. In each of the past 2 or 3 semesters, I think almost 70% of the students got some version of an A, but not a single person got an easy grade. They worked for it. Our job as staff is to try to make sure that you actually achieve this grade, and we'll do everything we can in our ability to do so, because that is essentially a hallmark of someone who has learned the subject and who we are comfortable releasing into the world as somebody who we think has some expertise in deep learning. We have a whole bunch of resources, the TAs. All the TAs are currently logged in to Zoom. So you should, and if you go into the participant list, the first bunch of 20 odd people are all TAs. Please look up the names. You have study groups. Each study group is going to be assigned a TA mentor. We do encourage collaboration. We have about 40 office hours every week. You can use those. Piazza, of course. And then I'm always available. So my policy is that rather than have an office hour, I let people just walk into my office. If I have time, I will talk to you. Otherwise, I'll make time. So always feel free to approach me. And then, of course, because of our collaboration policy, you can work with your classmates and friends. Of course, it's going to be stressful. There's a lot of work. So if you're under stress and unable to perform, please reach out to your TA mentor. And if that isn't getting any resolution, reach out to me. One way or the other, we will do our best to help you. Every Saturday, 2 to 5 p.m., we're going to have hackathons. Now, deep learning is not just a theoretical topic. There's a lot of hands-on work. And so you have a lot of homework assignments. Now, in order to facilitate getting these things done properly and to ensure that you're able to benefit maximally from not just your own study, but also those around you, we arrange hackathons on Saturdays where students are welcome to come in. They're not mandated, but they're welcome to come in, and ideally you will come in with your study group. There will be TAs monitoring and supporting the hackathons. You're allowed to discuss with other students and groups to help you with your assignments, and you can sit there and get things done. And it is our experience that students and teams who actually attend these hackathons get things done much more effectively and quicker than those that don't. And hackathons are also a great place to meet fellow students and form study and project teams if you don't have one already. And the first hackathon is this Saturday. Again, Saturday, 2 to 5 p.m., Rashid Auditorium. There will be pizza, just as an additional attraction. Our course objectives are that by the end of the course, you will be able to do these 3 things. Understand some of the theory behind neural networks. You should be able to build your own neural network components and tools. So if you're stuck in the desert with no PyTorch and just basic numerical algebra libraries, by the end of this course, you should be able to build your own toolkit. You should also be able to work on large-scale problems. So When we speak of understanding the theory behind neural networks, the intention is that you understand some of the math, the what, the why, and the how, and the occasional history. And understanding the theory will help you contextualize bullets 2 and 3 below. Also, knowing the theory will help you develop and extend your own ideas on the topic, which is great for research, which is great for grad school applications, and obviously it's great for job interviews. Now, when it comes to building your own neural network components and tools, you learn how to do these through the part 1s of your homeworks. There are 4 homeworks. Each has a part 1 and a part 2. The part 1s and the bonus problems associated with it teach you how to build things from scratch. And this is going to be an invaluable tool for you. And for being able to work on large-scale problems, the part 2s of your homework are what address these. In each of the 4 homeworks, you'll be given a fairly significant problem where you're expected to achieve close to state-of-art performance on some real tasks. And then, of course, if you're in 11785 or even 685, you're going to have a course project or the equivalent assignment. And course projects may relate to any of these 3 objectives. My lecture style is verbose. I use lots of visualization. Many slides with a lot of animation. I do not like to derive equations on the board symbolically because I have found that these things are kind of transient. They don't, what you see, when you see an equation being flashed in front of you for maybe 15 seconds, it doesn't quite read. If I explain it with a picture, you understand it much better. So given a choice between deriving an equation symbolically and explaining it with 30 slides of pictures and animation, I usually choose the picture route. If you don't like this form of instruction, then this class will not work for you because this is what I'm going to be doing. We want participation in class. So we're going to use various mechanisms. We'll use in-class polls for class participation. You're going to have some today. You'll have multiple polls posted at random times throughout the class. The polls will be posted on Piazza, except when I'm having a Zoom-only lecture like today where the polls will be on Zoom. And you're expected to respond to all polls. We don't score you on correctness because, you're still in the process of just learning this material, but we do score you on whether you respond. Now, every one of you is expected to attend the lectures. Some students have permission to view videos instead. And these are students who are in horrible time zones or may have some conflicts that they have notified me about. And so I have given them permission. Students who have permission to not attend the class and watch the videos instead must watch MediaTek videos. And these are going to be linked on the course page. And the nice thing about MediaTek videos is that they tell me who attended the lectures and for how long and from when. And so we are going to use this information to reduce their attendance. This is an interactive class. We like lots of questions. There's no such thing as a silly, wrong, or embarrassing question. And remember that if you have a question, the odds are that other people also have the same question. So you must ask, because even if you think it's kind of silly and naive, it isn't. When you have a question and you have not understood something, what this really tells me is that I haven't succeeded in conveying that concept to you properly. It usually also means that there are several others just like you who have the same question. So do not feel embarrassed. There's no such thing as a silly, wrong, or embarrassing question. Ask them, and I have infinite patience. I will try to reply or answer all of these to the extent I can. I won't always be able to answer them, but I will try. And I'm going to try different tactics to encourage our interaction. For instance, I might just assign numbers to all of you and just call out numbers. These numbers will be assigned to both students in the classroom and on Zoom. And when your number is called, you will be required to answer whatever question I've asked. Also, research has shown that physical actions that are taken in class actually increase student understanding and participation. So I'm going to do some strange things. I'm going to ask you to raise your hands. I'm going to ask you to shout out things in chorus. And these may look silly, but these things are predicated on practices that are actually recommended and are intended to keep you focused. These, if you see these occurring in class, do not be surprised. Do not find them strange. It's part of the discipline of trying to make sure that I impart as much information as I possibly can. Now, not everybody finds these things, pleasurable. So here is a student who was really pissed off a couple of semesters ago. He calls me one of the rudest professors he had in his university studies, and primarily because I try to get students to pay attention in class, and well, you have to live with it, right? The classroom is a dumb classroom. Now, I expect all of you to be paying attention. You will not be looking at your phones unless you're using it to answer class polls. You will not have your laptops open, except if you're using class polls, answering class polls, or trying to view or mark up lecture slides. If we find you using your devices for any other reason, you are a distraction, not just to yourself, but to everybody around you, and we may ask you to leave the classroom. I can't do that on Zoom, but then we are trusting you to actually pay attention, because I know that it's hard to stay focused for 80 minutes, but it's essential, right? You're going to be putting in a lot of effort to take this class. It does not make sense to get distracted easily. Please pay attention and stay focused. And here's something I shouldn't be saying, but I'm forced to. I'm physically handicapped. My back and neck are bent. I can't raise my arms. On some days, I cannot walk. My breath runs out halfway through a lecture. So this means I have some strange mannerisms. I can't raise my arms and clip on a mic on my jacket or shirt. I'm going to ask my TAs to do it for me. I use strange devices to point at the board because they are light, because I cannot raise my arm enough to point. And students have found these actions to be unacceptable in the past for whatever reason. I can't help it. If you cannot deal with it, then this is not the class for you. And so I'll pause here and I'll take any questions before I continue. Any questions? Questions, anybody?
I have one question.
Yes.
Some people are in the classroom and we didn't know it was on Zoom. Will it be the same for this week, or is it just?
So we had posted repeatedly that the class for the first week's classes would be on Zoom. Did you not get the note?
No.
So this was posted on Piazza. Please follow Piazza, because all of our notifications are going to be on Piazza.
Okay, thanks.
So this first week is the only week where the class is going to be on Zoom, because I'm currently in India. I have some engagements here at IIT. Once that's done, I'll be back on Saturday. And so the lectures from next week will be in person, unless, I'm going out for something, in which case I will let you know.
All right, sounds good. Thank you.
Any other questions? All right, I'm assuming there are no more questions. So without further ado, let me begin, right? Here are today's lessons. We're going to have a brief history of neural networks. We're going to go through a brief history of neural networks, about connectionism and its relation to cognition and the brain. We're going to look at early models and their limitations. And I'm going to introduce modern neural networks and what they can compute. And here's the reason all of you are in this course. Neural networks have by now become the main approach to AI, not even one of the main approaches. The latest successes are mind-blowing, right? They have been successfully applied to various pattern rec, prediction, and analysis problems. And in many problems, they have not just established the state of the art, but they have blown out the competition. They have achieved performances that were considered unimaginable just 5 years ago. So here are some instances of how that happened. This entire explosion with neural networks is actually very recent. You can trace it back to just 2016. People have been trying to build automatic speech recognition systems since the 1950s. We've had a lot of very complicated models, and much of the speech rec technology actually was born here in CMU. In fact, the entire field can validly be claimed to have started at CMU. But as of 2015 or even mid-2016, the performance of speech recognition systems was really pretty abysmal, more meant for party games than for anything useful. But then in 2016, October, Microsoft released this press release. They had finally built a system, speech recognition system, that outperformed human beings at a speech recognition task. This was the first time this happened, and that was because they used neural networks. Or machine translation. We've been trying to translate from one language to the other again for well nigh 40 years. But then in early 2016, it was still pretty much a joke. We used to mostly used for getting laughs. You translate something from English to Spanish on Google Translate and translate the Spanish back to English, compare what went in and what came out, and laugh like anything. And then suddenly, in about October or November 2016, something extraordinary happened. Google Translate actually began functioning so well that professional human translators found it advantageous to use it to perform the first cut of translation. What happened? In November 2016, Google switched to using neural networks. Or here's another thing. This is a pretty complex picture. I think this is the corner of Franklin and Broadway in New York. I may be wrong. And it has lots and lots of objects, and a AI system has managed to segment out every object, or almost every object. It did miss this trash can here. It has managed to segment out almost every object and identify it with high accuracy. Now, this kind of performance in 2015, it would have been unimaginable. These days, this performance is not even close to state of the art. We are much better. Or here's another thing. For the longest time, the metric for or the way to validate artificial intelligence was assumed to be mind games like chess and Go. We thought that if a machine was truly intelligent, it would be able to play purely intellectual games of the kind that we play, like chess. And then in the late 80s, we suddenly built a first system that beat human beings at chess. Does anybody even know where the first computer system to beat a human grandmaster at chess was built? Anyone? Does anyone know?
Yeah, I think it is Deep Blue.
It was called Deep Thought. It was actually built by Feng-Xing Su, I think, at CMU. It was they started this as a side project, but it became his PhD thesis, and it built a grandmaster, Lars Nielsen, I think, in 1989 in CMU. And then the same person went to IBM and then built Deep Blue, which is an extension which beat Garry Kasparov in 95. And after that, no human being has managed to beat the best computer games. So that particular hurdle was passed. But then Go remained a challenge. And that's because Go is extraordinarily more complex than chess. Chess has about 10 raised to 120 states. Go has 10 raised to 180. And so we just kept imagining that, sure, we managed to do something for chess, but computers, they are never going to beat humans at Go. And then 2016 again, magic date, AlphaGo beat a world champion at Go. And after that, no human being has managed to beat the best Go systems. These days, you can actually pick up a Go system which knows nothing and starts learning from scratch. And within a few hours, it can beat the world champion, human world champion. It just learns. And this has been made feasible using neural networks. Or here's another thing also from 2016, images that were captioned. Man in black shirt is playing guitar. Construction worker in orange safety vest is working on a road. Two young girls are playing with a Lego toy. Well, the second one is not a young girl, but it's, fairly close. Boy is doing a backflip on wakeboard. Now, all of these are captions that you could imagine were actually generated by a human. And when this first came out, it blew people's minds. Nowadays, the modern latest systems can outperform these. This is a very rudimentary system by modern standards. But this came out in 2016 also. And then, of course, now things have simply ballooned, right? Here's to the left is a picture of a bowl of soup that looks like a monster made of Play-Doh, which was drawn by Dali based only on this description. And it looks like something, a human artist might have painted. Or here's another one. Only yesterday I asked Bing, which is ChatGPT, why does winching up an anchor raise the anchor instead of pulling the ship down? It understood the context. It gave me a perfectly good scientific answer to this, along with citations. And this is just made possible again by neural networks. And so neural networks have basically taken over every field, from astronomy to healthcare, even predicting stock markets, everywhere, you name it. They are the state of the art. So what are these magical neural networks? Now, from where we stand in the course right now, they are these magical boxes into which things go in and useful stuff comes out. Like a voice signal goes in, a transcription comes out. An image goes in, a text caption comes out. Maybe a game state goes in and a suggestion for the next move comes out. That's all it is. But what's in these boxes? Now, to address this problem, we recognize that all of these actions that we just saw, these activities like recognizing speech, captioning images, playing games, they are fundamentally human actions powered by human intelligence. And so in order to understand how that works, maybe the place we should look is the seat of human intelligence, namely the human brain. Or even before that, cognition. Human beings have this amazing ability for cognition, which is what the brain produces. By the way, this is a picture of the Thinker by Augustin Rodin. Does anybody know who this statue represents? Anyone? Just curious. Has anyone seen this? Please seen this one in Paris? I guess not, right? Okay. So that one's supposed to be Dante Alighieri. But anyway, here are our magical cognitive abilities. Here are the things human beings can do. We can learn. We can solve problems. We can recognize patterns. We can create. We can just cogitate. We can just sit in one spot and think and dream and cook up new things with no input whatsoever. So these are these amazing abilities that make us who we are. So if we want to build a computer, an artificial system, which can behave like us, maybe these are the abilities that we must be trying to emulate. But then how do we actually perform these acts? How do human beings work? How does cognition happen? The problem, as Marvin Minsky once said, is that if the brain was simple enough to be understood, we'd be too simple to understand it. But then that hasn't stopped us from trying. And so people have been trying to understand how cognition works literally for thousands of years. The earliest theories of cognition go back to Plato in 400 BC. So does anyone here recognize this painting? Anyone? You guys are awfully quiet. I'm sure someone here has seen this painting. Anybody at all? None. Okay. This is a painting called The School of Athens by Raphael, painted around in the 1500s. And it's supposed to include most of the notable scientists through the ages, right until the 14th or 15th century. And so here is Aristotle, and here's Aristotle, and here's Plato. Anyway, Plato actually introduced the first recorded theory of how cognition works was by Plato. It was called associationism, which states that humans learn through association. And this is the theory that continued to stay the most active theory right through the early 1900s. And The proponents included not just Plato, but the 18th century scientist David Hume and even Ivan Pavlov. So what is this notion of associationism? What are associations? Associationism literally states that we associate percepts with one another. For example, in our experience, lightning is usually followed by thunder. So after exposure to these percepts for a while, we begin associating lightning with thunder. And then when you see a bolt of lightning, you expect, I'm going to hear thunder. Or alternately, if you hear thunder, you're going to think a lightning must have struck somewhere. So you've made this association. Now, and of course, this theory, there were lots of the actual theoretical framework itself gets a lot more complex. Everybody's familiar with Ivan Pavlov's famous experiment with the dog, where he would ring a bell and the dog would drool expecting food. And as it turns out, associationism is actually a pretty darn good theory for how the brain works. And in fact, a lot of machine learning, even today, is based on this notion of associations between percepts or associations between inputs and outputs. That's all very fine, but it still doesn't explain the brain. How do we do it? Where are those associations stored and how? So the first insight into this problem was perhaps obtained in the mid-1800s. By the mid-1800s, the science of microscopy had become so advanced that we were able to look into the brain and we knew how it was constructed. And we knew that the brain was just a mass of interconnected cells of a special kind of cells called neurons. And within the brain were all of these large numbers of neurons. Each neuron had this connected out to many other neurons. And each neuron had incoming connections from many neurons. And so the entire brain was a network of these neurons. Fine. The brain is a network of these neurons, but how does that enable cognition? That theory was first proposed by this guy, Alexander Bain, in the 1870s. So Alex Bain, like in the 1800s, most scientists were polymaths. They were good at a whole lot of things. And so Alex Bain was a philosopher, a psychologist, a mathematician, a logician, a linguist, and a professor. That last one might have been the hardest because in those days it was much harder to be a professor. In 1873, he wrote this book called The Mind and Body, where he proposed that the manner in which the brain stores associations, the manner in which the brain stores its information is through the connections between the neurons. That all of the information between the relationship between percepts, or more generally between stimuli and response, was actually stored in the manner in which these neurons were connected. So this was the first connectionist model, and this dates back to 1873. And Alex Bain even came up with actual example models. He actually drew these circuit diagrams. Here is one of these diagrams. Here you have a single network, and the same network produces different outputs for different inputs. Now assume that all inputs and outputs are binary, Boolean, 1 or 0. So in this network, if A and B are active, I'm going to say if they fire, then X fires. If A and C fire, Z fires. If B and C fire, Y fires. So the same circuit, but different combinations of inputs produce different outputs. This is something that seems very commonplace to us. But in the 1870s, this was considered almost a heresy. This was kind of strange. Or here is another circuit that Bain proposed. Here, the output actually depends on the intensity of the incoming signal. So output X combines 2 responses. Output Y combines 3 responses. So if you have a short duration, high intensity response, then X will fire, but Y will not. But if you have a longer low intensity response, Y will also fire. So basically, the kind of response depends on the intensity of the excitation. And not only did he propose these circuits, he also came up with ideas of how these connections could learn their strengths. So here's what he said. When two impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. Basically, he says that if the triggering of one nerve causes another nerve to trigger, then the connection between the two gets stronger. This predicts Hebbian learning, and actual theory of Hebbian learning was not going to be proposed for another 75 years. So Bain was almost 75 years ahead of his time. Now, the problem was that Bain's cohorts of his time thought he was talking nonsense, that all of this just didn't make sense. And they were so certain in their doubt that eventually they made Bain doubt himself. And as Bertrand Russell says, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure, while the intelligent are full of doubt. And so in 1873, Bain postulated that there must be 1 million neurons and 5 billion connections to obtain 200,000 acquisitions of percepts. Then 10 years later, he began thought harder about it, and he said that this only talks about fully acquired concepts. What about the partially formed associations? You need more neurons to even to begin forming these associations. So obviously 1 million and 5 billion is not going to be enough. And by the end of his life, he did some math, and he said that for the brain to hold all the information it currently does, this mechanism doesn't make sense. It's too complex. The brain would need too many neurons and connections, and he recanted his ideas. Well, he was right in 1873. He was wrong in 1903. Does anybody know how many neurons the brain actually has? Anyone? Anyone at all? About 100 billion. 80 billion is the correct number, right? So the brain has 80 billion neurons and 100 trillion connections. It has more than enough capacity for everything Bain thought it would need, it could do. And so, in fact, it's Bain's connectionist theory that still remains. The brain is a connectionist machine. It is a network of simple elements. Each neuron by itself is not very complex, but the information capacity of the brain and the processing capacity of the brain is captured through the connections between these units. And so modern connectionist machines emulate this structure. Your artificial neural network emulates the structure. So here's what a connectionist machine is. It's a network of simple processing elements, and all world knowledge is stored in the connections between the elements. Now, that's a connectionist architecture. Does anybody know the kind of architecture of the standard processor you find in your computer or in your cell phone? What's it called? I'm sure we have some electrical engineers here, or people who are computer scientists who can answer this question. OneNman architecture. What's special about a OneNman architecture, Alex? So how does that? Or anybody else? Can you tell me? Nobody? Okay, exactly. Alex is right? So in the von Neumann architecture, the processor is separate from the memory. And the processor data and programs are stored in the memory, and the processor reads things from memory to perform tasks. So there are sub-architectures. There's the Harvard architecture where you have different memories for programs and data. You have the Princeton architecture where program and data are both share the same memory. Modern processors are a combination of the two. So they have Harvard architecture inside the processor, but the main memory is Princeton. It doesn't matter. The point is, you separate the processor from the programs and data. And so If you want to change the program, if you want the processor to perform a different program, you just load a different program in the memory, and the same processor can now perform this new task. And that's what makes these machines so very versatile. Your little PDA can perform hundreds of different tasks simply because you can just load different programs in memory. In the connectionist machine, this becomes impossible. In the connectionist machine, the program is the architecture because all the workings of the program are encoded in the connections between the units. If you want to change the program, you have to change the entire machine, which is why we don't really build neural networks in silicon. It's very inefficient. Rather, we actually emulate neural networks on OneNman machines. So here's a quick recap of everything we've discussed so far. Neural network AI-based AI has taken over most tasks. Neural networks originally began as computational models of the brain, or more generally, models of cognition. The earliest model of cognition was associationism. The more recent model of the brain is connectionist. Neurons connected neurons, and the workings of the brain are encoded in these connections. And current neural network models are connectionist machines. So, any questions? From any questions? None? We have our first poll, and let me launch the first poll. Can you folks see the polls? So associationism and connectionism, I can try to do that, Sebastian. All right, guys. There are 70 people who haven't yet replied. I'm giving you 5 seconds before I close the poll. Okay, thank you. I'm stopping this poll. And of course, the answer, as we just said, was Alex Bain, right? Anyway, to answer your question, Sebastian, associationism is a theory of how we relate concepts and how we come up with inference. So Alex, yes, the in-class polls will be on Piazza. So it doesn't really tell you how the whole thing works. Connectionism is a theory of how the brain actually works. The connectionist architecture performs associationism. You can think of it that way. Did that answer your question, Sebastian? Thank you. All right, let me move on. So I'll explain. Oh my, there was a second question. I forgot to release the second question, but how many connections exist between neurons in the brain? 100 trillion, right? Okay, that's a mess. So here's what a connectionist machine is. It's a network of simple processing elements. All world knowledge is stored in the connections between the elements. But what are these individual elements? For that, we're going to go back to the brain. The brain is composed of neurons. And here's what an individual neuron looks like. It has this head which surrounds the nucleus. It's called the soma. The soma has many of these little tendrils coming out called dendrites. And the dendrites are the connections through which signals come into the neuron. Now, when the total signal inside the neuron from all the neurons it's connected to exceeds some threshold, then the neuron generates a spike train. And the spike train it generates, the strength of the spike train is going to be proportional to the total incoming signal. And that goes out through this long leg to other neurons downstream. Now, here's something that's interesting. This long leg is called the axon, and the ability of our body and our brain to function depends critically on the safety of this axon. If this begins to get damaged, you're going to be your brain is basically going to die. And so this axon is protected by a sheet of fat called the myelin sheath, which is produced by something called glial cells. And there's a bunch of scientists who like to work on this kind of things, and they have taken possession of Einstein's brain, and they've analyzed it, and they found that the difference between Einstein's brain and normal people's brain is not that he had more neurons in his head. He had a lot more glial cells, a lot more fat in his head. It turns out that if you have more fat in your head, the connections are more protected, and your brain functions better. And so people with more fat in their head can be expected to be smarter than people with less fat. So when someone calls you a fat head, they're actually giving you a compliment. You may not have thought about it. And here's another thing. Because the connections are so key, the brain's neurons cannot undergo cell division. When they undergo cell division, the connections will break. So neurons are only formed from stem cells. And this is a process called neurogenesis, which occurs when you're in the womb and in the early stages immediately after birth. And after that, it just kind of grinds down to almost a halt. So when you're 2 days old or 1 month old, you have almost all the brain you're ever going to have. And after that, it's a long way down. Anyway, so here we have the neuron, right? How do we computationalize it? The first guys to come up with a computational theory for the neuron were these two guys, McCullough and Pitts. McCullough was a professor in the University of Chicago, and Warren McCullough and Walter Pitts was a homeless guy who just wanted to be a logician, who just wandered around and one day knocked on McCullough's door. And so here are their pictures. Does anybody want to take a guess? Who is McCullough and who is Pitts? Okay, Alex, thank you. That is indeed true, right? So the guy to the left was very young when he ended up in McCullough's office. He was maybe 16 years old, Walter Pitts. And they came up with this model, this fantastic paper, W.S. McCullough and W.H. Pitts, a logical calculus for the ideas immanent in nervous activity, published in 1943. And here is the computational model they came up with for the neuron. So this triangle itself represents the neuron. This outgoing line is where the signal produced by the neuron goes out of. These colored lines are the lines coming into the neuron, and the connections are synaptic connections. Now, incoming connections are of two kinds. These are the excitatory connections, which are shown by the green line. Each excitatory connection has a strength. The weight, you can think of it as a connection weight, and the weight is equal to the number of times it connects to the neuron itself. So this connection has a weight of 2. Inhibitory connections have a strange property. So long as they are not active, the neuron can function. But if there's any signal coming up the inhibitory neuron, then the neuron is always going to produce a 0. It's not going to produce any output. The entire thing is Boolean. Incoming and outgoing signals are Boolean. This was their model. And they showed that using this model, you can perform all kinds of Boolean logic. Now, the connection itself has a delay. So here is an instance where neuron 1 generates signals, and 1 instant later, those signals arrive at neuron 2. Neuron 2 will fire if the total input is equal to or greater than 2. So there's a threshold. And if the total input matches the threshold, then the neuron fires. That was the McCullough and Pitts model. And so this is just a delay. Anytime neuron 1 fires, 1 instant later, neuron 2 fires. Here's one. This neuron is going to fire if the total input is equal to or greater than 3. What is this gate? Can anyone tell me? What would this gate be? Anyone? That's an AND gate, right? Because you need both 1 and 2 to fire. Only then will the total input be 4. Otherwise, it's going to be 2, and this is not going to fire, right? So what about this one? Actually, no, this is neuron number 3. In every case, the threshold is sorry, I got this wrong. In every case, the threshold is 2. So this is an OR gate. If either of these fire, this guy is going to fire. Here, you need both 1 and 2 to fire. So this is an AND. Pardon the mistake, right? I got confused by the number here. And so what do you think this guy is? What would this be? Anyone? It's not just a NOT. 3 will always fire if 1 fires, unless 2 turns on, because 2 is inhibitory, right? So it's going to be 1 and not 2. 3 is only going to fire if 1 fires and 2 doesn't fire. So it's 1 and not 2. It's a more complex Boolean operation. So you can see that it's a more complex Boolean operation, basically. 1 must fire and 2 must not for 3 to fire. It's 1 and not 2. So we have delays, we have the OR, we have the AND, and we have more complex Boolean operations. We can get NOTs. And they showed that using these gates, you can have even more complex responses. So here is a model for heat and cold sensation. Now, this is a heat receptor. This is a cold receptor. If the cold, now here's something that we have all we've all experienced. If you touch something very cold for a very brief period of time, the instant response you get is not of cold, it's of heat. You have to keep touching it to realize that it's cold. And their model, they came up with a model for it. So here, if there's a heat receptor, a cold receptor, heat sensation, cold sensation, if the cold receptor fires very briefly, then one, yes, that's right, they're only identifiers. If the cold receptor fires very briefly, then 1 instant later, this guy's going to get 1 signal from here. But then 1 instant later, this guy is also going to fire. But for this signal to come here, it's going to take a second instant, right? And so because this is going to take a second instant, if the cold receptor is very brief and just 1 instant long, this will either receive 1 signal from here or 1 signal from here, but it will not receive 2 signals. So you don't get a cold sensation. On the other hand, if your cold sensation is extended, then in the second instant, 2, this will fire. And so this guy is going to get 1 response from here and a response from 2 instants ago from here, and it's going to fire. And so this cold sensation neuron will only fire if the cold sensation is extended. On the other hand, if you have a very brief cold sensation, 1 instant later, if you have an extended cold sensation, this inhibitory connection is going to prevent anything happening from here. But if you have just a very brief cold sensation, 1 instant later this fires, 2 instants later this fires, 3 instants later this fires. So this model shows you how just touching something cold will give you a heat sensation, but keeping your finger on it will not give you a heat sensation, it will give you a cold sensation. So it's a pretty powerful model. And they came up with many more such explanations. It's beautiful. But then the problem was it was incomplete. They claimed that their model can compute a small class of functions, which is true. These are finite state machines. They claim that if a tape is provided, their networks can compute a richer class of functions and be equivalent to Turing machines, which was also true. But for many of the results they claimed, they didn't actually prove them. And the biggest problem was they said this can do this, all of this, but how do you learn these connections? How do you know how many synaptic connections one neuron must have on another to make it all work? They didn't come up with a mechanism for it. For that, we had to wait for this guy. So this was Donald Hebb, another interesting character. He was Canadian. He initially trained to be a novelist. Then he decided he really wanted to be a farmer. Then he decided he didn't want to be a farmer. He wanted to be a hobo. So he became a hobo. And then that didn't work for him. So he decided he'd be a school teacher. That didn't work for him. So he went off to Harvard and did a PhD and became a psychologist and then worked at various places. Interesting guy. And in 1949, he wrote this fairly revolutionary book called The Organization of Behavior, in which he proposed a mechanism whereby neurons could learn the weights of their connections. Here's the learning mechanism. When an axon of a cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells firing B is increased. It's a very complicated sentence, but what it says is that if there are two cell neurons A and B, and the firing of A results in the firing of B, then the connection between the two becomes stronger. So neurons that fire together, wire together. So here's a better visualization. So to explain the Hebbian idea of how neurons learn their connections, this picture shows the connections between two neurons. Let's call them neuron X and neuron Y. Now, neuron X's axonal connection connects to the dendrite of neuron Y. Now, they don't actually touch one another. Neuron X's axonal connection ends in this bulb. It's called a synaptic knob, which is actually a small distance from the dendrite of neuron Y. And whenever a signal comes down to this bulb, it releases a bunch of chemicals called neurotransmitters, which excite neuron Y. And if the excited or a signal in neuron X successfully excites neuron Y, then this knob becomes a little bigger and the connection becomes stronger. So this is the biological mechanism. But then if you put math to it, this says if neuron X repeatedly triggers neuron Y, the synaptic knob gets larger, so the connection gets stronger. If I say that the weight of the connection between neuron X and Y is WXY, then anytime X is 1 and Y is also 1, it means the two have fired together, and this weight must increase. That can be written as this mathematical rule, WXY equals WXY plus eta times XY. Eta is the amount by which the weight increases, and this increment only happens when both X and Y are 1. So it captures this Hebbian learning mechanism. And it's a brilliant formula. It's actually the basis of many learning algorithms in machine learning, but it has one flaw. Can someone point out the flaw? What is the flaw with this? Anybody? Linear, unbounded. That's the answer. Thank you. So Arav, that's the answer. This does not, it's unbounded, right? The weight always only increases. So if you wait long enough, eventually everything, things are going to saturate, right? Eventually everything will end up connected to everything, and it's going to become a useless machine. Stronger connections keep enforcing themselves. There's no notion of competition. There's no reduction in weights. So this is the problem. And people came up with various kinds of modifications for it, generalized Hebbian learning, Sanger's rule, blah, blah, blah. But this problem remained. We need a way for weights to actually become weaker, right? And this doesn't provide it. So all of you guys are right. James, Theron, you guys are right? Perfect. And so let's have our second poll this time. I'm going to release poll 2. Can you see the polls? So Richard, randomly, you will have neurons just firing together, right? But when two neurons randomly fire together, the connection becomes stronger. And so if you wait long enough, pure noise can simply make the whole thing really strong, right? As you wait long enough, everything is just going to saturate. Did that answer you, Richard? Richard, did that answer you? Okay, so why not set an upper bound? That's the whole thing. If you set an upper bound, the ones that are upper bounded will stay within the bound. The ones that are below the bound will keep increasing until they meet that upper bound. And that is the issue, right? So decrease the weight. Okay, so let me stop this. I think most of you got the answer. It's fundamentally unstable because there is no reduction in the weight, right? So yeah, what we need is a better mechanism. And that mechanism was provided by this guy, Frank Rosenblatt. Frank Rosenblatt was a brilliant guy who came up with what we now know as the perceptron. He was a psychologist and a logician in Yale, and he invented the perceptron in 1958. His life is kind of tragic in that he went out to celebrate his 42nd birthday on a lake and drowned. And it's one of those losses which was a tremendous hit to science. But then he came up with this model, which he called the perceptron, which was his equivalent computational model explaining perception, specifically meant for explaining visual perception. So you have the retina, and then you have this complicated structure where you have many connections from the retina to one set of units here, which connect to a second set of units here, which then connect to response units. But then if you sort of simplify the picture, here I only have one row of blue circles, but if you look at this figure, there are actually two in this one, right? They're called association and projection areas. This is the simplified model. His model said there are lots of sensory units. These could be the cells in your retina, and there's a layer of cells which respond to these guys, and their response could go to another layer of such cells, which are not shown. You can have any number of layers, and then finally their connections go off to these red units, which are the response units. So this was the entire model, Rosenblatt's model for how perception works. And he called this the perceptron, but then something unfortunate happened. People began using the word perceptron to describe these individual colored units rather than this entire picture. And so now the focus for the rest of our lecture is on this individual unit. What does that individual unit look like? Each individual unit is exactly as a simulation of the nerves in our brain. The unit gets a collection of inputs. Each input has an associated weight. And if the weighted sum of all of these inputs exceeds some threshold, the unit fires. It produces an output 1. If it doesn't exceed the threshold, it produces an output 0. So if I were to write it in math, I can write it like so. The output y is 1 if the weighted sum of inputs minus the threshold is non-negative, otherwise it's 0. Is this picture making sense to you guys? Again, I need you to give me a thumbs up if it makes sense. I'll wait for 100 of those before I continue, because everything hinges on understanding this picture. So only I have 2, so okay. I'll wait. So this is key. Right. Out of 270 students, only about 90 have said yes. So what did I miss here? Okay, I'll assume that everybody got it. Okay, so here's the model, right? So you compute a weighted sum of inputs and compare it to a threshold. If it matches or exceeds the threshold, the output is 1. Or I can write it like so. The weighted sum of inputs minus the threshold must be non-negative, right? So that's a very simple model. Now, Rosenblatt originally claimed that his larger model, shown in the top right over here, could represent any Boolean function and perform any logic. At some level, he was actually right. But then the media went crazy with it and then ran away with it. And here were some reports that came out. The embryo of an electronic computer that the Navy was funding him, expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. New York Times, 1958. Frankenstein monster designed by the Navy that thinks. Tulsa, Oklahoma Times, 1958. And they kind of went overboard, which is always a bad thing, because your results will often not match the hype. But the worst thing that happens, no, there will not be. So is that instead of thinking of this entire structure as the perceptron, this lower structure, the simplified individual unit, began to be called the perceptron. And so people sort of assumed that the claim was about this individual unit. Now, the fact is that this individual unit of Rosenblatt's is in fact incredibly powerful. You can compute a whole lot of Boolean functions with it. Just this one unit, which compares a sum of weighted sum of inputs to a threshold. And moreover, you can actually learn these weights to make this unit compute any given Boolean function. You may not be able to do it successfully, but there's always, it even has a learning mechanism. And in fact, Rosenblatt came up with this learning mechanism. Here's what it is. So he said, and here he introduces the notion of supervision. He said that each unit has a desired output in response to some input. This is something that was missing in Hebb's rule, right? And if a connection, if you consider any particular connection, if an input produces the correct output, there's really no need to be modifying the connection. The neuron is already doing the right thing. On the other hand, if the output is wrong, then you want to change the weight. And how do you change the weight? If the output is greater than the input, then you want to decrease the weights so that the total input decreases, right? So, and the output goes down. If the output is smaller than the desired output, so when the output is greater than the desired output, you want to change the weights. When the output is smaller than the desired outputs, you want to increase the weights. So this looks a lot like the Hebbian rule, except that it says that the weight is modified by a factor that's the product of the input and the error, not just the output, but the error between the desired output and the actual output. Now, all of these variables, the x's and y's, they're all Boolean in the original model. So the desired output would be either 1 or 0. The actual output would be either 1 or 0. And so this difference is going to be 0, 1, or -1, or 1 or -1, right? So which means that the weight can either stay the same, get incremented by eta, or decremented by eta. This is a clear update on Hebb's rule. And you can also show that this very simple unit can compute all kinds of functions. So yeah, in this model, we are assuming that everything is Boolean, but we'll move on, right? So let's see how it can compute Boolean functions. So in these figures, the number written on top of any arrow is the weight of the connection. The number inside the circle is the threshold. In this particular unit, if X alone fires, the total input coming in is just 1. This will not fire. If Y alone fires, the total input coming in is also just 1. It will not fire. You need both X and Y to fire. And only when both X and Y fire is the total input going to be 2, which matches the threshold, and this unit will fire. So what is this Boolean gate? Can anybody tell me what is this gate? That's an AND, right? What about this one here, the one to the right? That's a NOT. If X is 1, the total input is -1, this won't fire. If X is 0, the total input is 0 and will match the threshold and it will fire. The one at the bottom, it's a NOT. Fantastic, right? You can show that this unit can mimic any Boolean gate. And in fact, in the next class, we'll see it can do a whole lot more. But what it cannot do is model the XOR. There's absolutely no setting of weights which will permit this model to compute an XOR. I'll let you think about why this is. And if you don't figure this out by the end of this class, we'll see this in the next class. But then, how do you make it compute an XOR? Then you go back to the brain. In the brain is not just one neuron. It's a network of neurons, right? The individual elements are weak computational elements. You need networking. And so if I just connect up 3 of these neurons, like so, I can compute an XOR. These first 2 neurons connect directly to the input. This neuron on top computes X or Y. This neuron on the bottom computes not X or not Y. This neuron over here and these two outputs. And yes, the weights can be negative, right? As we saw over here in the case of the knot. And because the weights can also decrease. And so this complete network of 3 units is now able to compute the XOR of X and Y. Now let's introduce some terminology over here. These are the inputs often called, this has got multiple perceptrons connected in layers. So this is called a multi-layer perceptron. The actual output is received by this, is read off this perceptron. So this is called the output perceptron or the output layer. These guys, you don't need to know what their individual outputs are. You're only interested in the output of this one. So you call them the hidden layer. You can hide them and nothing changes. But the key point is that by connecting up these perceptrons in a little network, I'm able to compute the XOR. It gives us another lesson. By connecting these up in a network, I'm able to compute more complex Boolean functions. In fact, I can compute arbitrarily complicated Boolean functions. So in cognitive terms, it means that I can connect up these perceptrons to compute arbitrarily Boolean functions over sensory input. So in other words, if I correct that. So in other words, if I form a sufficiently complicated network, sufficiently designed network of just these basic perceptrons, I can compute pretty much any Boolean function. Here, for example, is a network that computes this ugly Boolean function of these inputs. So a multi-layer perceptron is what is called a universal Boolean function. It doesn't mean that a single MLP can compute every Boolean function. It means that if you give me a Boolean function, I can always design an MLP that will compute it. And so the story so far, neural networks began as computational models of the brain. They're connectionist machines. They comprise networks of neural units. The McCullough and Pitts model modeled neurons as Boolean threshold units. This was revolutionary and started the entire cascade of work that followed. They modeled the brain as performing propositional logic, but they didn't give us a learning rule. Hebb's learning rule said neurons that fire together, wire together, was unsupervised and unstable. Rosenblatt's perceptron was a variant of the McCullough and Pitt neuron with a learning rule, and Rosenblatt actually showed that if the two sets of inputs or input combinations for which the output is either 1 or 0 are linearly separable, then the learning rule will finally give you a set of weights which will compute the Boolean function exactly. And so the Rosenblatt perceptron is a variant of the McCullough and Pitt neuron with a provably convergent learning rule. But then individual units are limited in their capacity. If you want to have more complex things, then you need multi-layer perceptrons, and they can model arbitrarily complex Boolean functions. But then, all of you are sort of itching with this question. We're not Boolean, right? We are working off real inputs, and we make non-Boolean inferences and predictions. So how does this model relate to our real-life experience? Easy enough. The same thing works with real inputs as well. Instead of having all the x's be Boolean, let's say all the x's are real. All the weights are also real. Even now, the unit is still going to perform the same action. It's going to compute a weighted sum of the inputs. If the weighted sum exceeds a threshold, the unit, I'm going to assume that the output is Boolean for now. So if the weighted sum exceeds a threshold, the unit will fire. Otherwise, it won't. So this is the same rule as before. I can rewrite it slightly. Instead of having a separate threshold over here, I can say instead that I'm going to compute a weighted sum of the inputs minus a threshold, or the weighted sum of the inputs plus a bias term, where the bias term is minus t. And then, so this basically I'm computing an affine function of the inputs. And this affine function of the inputs is going to be passed through what I call an activation function. And the activation function is specifically a threshold activation, which outputs a 1 if the value coming in is non-negative and a 0 otherwise. So this model is exactly the same as this guy here. I've just redrawn it. So do you see how this, can you guys see that these two are the same? Anybody? Just give me a thumbs up if you see that the two are the same. I'll wait for 100 of those before I can continue, because we're going to be using this, right? Okay, I think we have that. So, all right, let me continue. Right? And so what this is it's computing an affine function of the inputs and putting that affine function through a threshold activation. Does anybody know the difference between linear and affine? Anyone? What's the difference between linear and affine? Affine has an offset, right? Affine functions have non-zero intercepts. Exactly, right? So suppose I have something like, I'm going to try to write with my mouse. If I have a function which is, say, wi xi, right? This is a linear function. If I equate it to 0, then this is going to be the equation of a line or a hyperplane that goes through origin. On the other hand, if I add a bias term to it, where's my mouse? Okay. If I add a bias term to it, which is summation wi xi plus b, sorry, this thing misbehaves, but plus b, this is affine, and it's made affine by this bias b. And now if I equate this to 0, this is still going to be the equation of a line or a hyperplane. It will have the same slope as the linear function, but the intercept is not going to be through the origin. So we first compute a linear, an affine function of the inputs, and then put it through an activation, which is a threshold activation, which means the output is 1 for non-negative inputs and 0 otherwise. But then when you redraw it like this, you can go one step ahead. You can say I'm computing an affine function of the inputs and putting it through some activation function. The one that we've seen so far was the threshold activation. This was Rosenblatt's perceptron. But you could have other things like the sigmoid or these other functions here, or even others that we'll see later. But for today, I'm going to continue assuming this threshold activation, because this threshold activation conveys much of the intuition that we really need to develop. So now let's look at this function again. I'm computing a weighted sum of the inputs and comparing it to a threshold, or alternately an affine function of the inputs and putting it through a threshold activation. So I'm reverting to the simpler figure just for illustration. Here's the perceptron again. You compute a weighted sum of inputs, and if this exceeds a threshold, the output of why do we need the threshold activation? We're just using this. Okay, I'm using it for illustration, so hang with me, right? And you will see why it gives you really good intuition for why things work. So here is the function again. If the weighted sum of inputs exceeds a threshold, the output is 1, otherwise it's a 0. And the boundary between the two is where the weighted sum exactly equals the threshold, right? So this, when I say summation wi xi equals t, that's the equation of a line or a hyperplane, right? So the boundary between the regions where the output is 1 and the output is 0 is where the weighted sum exactly equals the threshold. It's the equation for a hyperplane. And so there's in 2 dimensions, that's a line. So there's this line. On one side, the unit produces a 1. On the other side, it outputs a 0. If I had 2-dimensional input and I were to draw this function, it's going to look like this Heaviside function. There's the line. On one side, the output is 0. The other side, the output is 1, right? If I were to use this for classification, then I can say that it draws a line and classifies everything on one side as the class 1, other side is 0. But then once you can do this, here's where things get interesting. Now, you can see why it works. The perceptron works as a Boolean gate. In Boolean functions, the inputs are all binary, either 0 or 1. So if I had 2 inputs, these are the only 4 combinations possible: 0, 0, 1, 0, 1, 1, and 0, 1. If I had a perceptron whose boundary was over here, what gate would it represent? What is this gate? Anybody? That's an OR. What about this guy? That's an AND. What's this? This is simply going to be a NOT of x1 and it's ignoring x2, right? So beautiful. And once you see this, you can also see why it cannot be an XOR, but we'll see more of that in the next class. But then let's begin putting things together, right? Let's say I want to build a network which outputs a 1 when the input is inside this pentagonal region and 0 outside, right? So no, the inputs are continuous. So, yeah. But in this example, I'm explaining how it works as Boolean gates. And for Boolean gates, the inputs are just either 0 or 1. But more generally, consider something like this. I want to build a network which has an output of 0 outside the yellow region and 1 inside. How would I do it? I start off with one perceptron, which captures this boundary. It outputs 0 below the line and 1 above the line. A second one, which captures this boundary, 0 to this side, 1 to this side. The third one captures this boundary, 0 to this side, 1 to this side. The fourth one captures this boundary. The fifth one captures this boundary. Guess what? The pentagon is the only region in which all 5 perceptrons are going to output a 1. So if I just sum all of their outputs and compare the sum to a threshold of 5, the output is going to be a 1 only when all 5 output a 1. That's inside this pentagon. For inputs anywhere else, at least one of these neurons is not going to fire. And so the output is going to be a 0. And voila, I have a network that exactly captures this pentagonal decision boundary. Questions, anybody? Anyone? No? Okay. Then I can do something more interesting. Now, suppose I want to have a decision boundary of this kind, where I want an output of 1 inside either this pentagon or this pentagon. How do I do it? Simple. I have one subnetwork for this first pentagon, a second subnet for the second pentagon, or the 2. And now I have a network which is going to output a 1 if the input is in either of these 2 pentagons and 0 otherwise. But once I can do this, I can get more complicated decision boundaries. How, for example, would I construct a network which captures this boundary? Anyone? How would I do this? Anybody? Exactly, right? I can just break this up into lots of little polygons, and it's not 3 hours. This is going to be a lot more complicated than that, right? So what I would need to do is to decompose it into a whole bunch of little units that can be modeled by a subnet and then combine those. Now, remember that the decision boundary is not necessarily always convex. So for example, if over here I used a threshold of 4, what would the decision boundary look like? If the threshold were 4 out here, what would the decision boundary look like? Anyone? Come on, guys. Kind of running out of time, so I'd like an answer. A star, right? Exactly. So it doesn't mean that the decision boundaries are always convex. But you can decompose this into a bunch of subregions, which can be modeled by a subnet and then compose the whole thing up. You can model any decision boundary. Now let's get to the problem of classification. What is the problem of classification? It's the problem of finding decision boundaries in high dimensional space. For example, if I'm classifying digits, I'd get a picture of this kind. This is from MNIST. It has 784 pixels, so it's a 784 dimensional input. That input would go into my network. Now, these inputs live in a 784 dimensional space. If I want to build a network which detects the digit 2, in the 784 dimensional space, there's a region, which I've shown using this peanut, within which all the 2's reside. And all I need is to construct a network which captures this decision boundary, and we just saw how. So multi-layer perceptrons are universal classifiers. You give me any classification boundary, and I can always construct a multi-layer perceptron that captures that classification boundary. It's because of the mechanism that I just showed you, right? I mean, the actual manner in which you do it might might have all kinds of tweaks to it. But the point is, an MLP can model any decision boundary. It's a universal classifier. So MLPs are connectionist computational models. Individual perceptrons are computational equivalents of neurons. And the MLP is a layered composition of many perceptrons. They can model any Boolean function, and they can model any decision boundary. So they are universal Boolean functions, and they are universal classifiers, right? So before I answer this question, let me release poll 3. I may go a few minutes over, guys, just bear with me. The first class is always a bit slow. Advait will deal with that next week. Poll 3 is not showing up. That's very strange. So that's a problem with Zooms. It shows up for some and not others. Okay, so let me end this poll, right? Can somebody answer me? How many threshold activation perceptrons will I need for a hexagonal decision boundary? Anyone? 7, right? 6 for the 6 boundaries and the 7th one for combining the lot. Perfect. So the answer is 7. Now, so we've looked at Boolean functions, we've looked at classification functions, but then your outputs are not all, the networks are not always performing classification. Our brain is performing predictive actions where the outputs are real valued. The inputs are real valued. Can we construct networks where the outputs are also real valued? Here's a quick view into how you might do it. Here's a little network. I have 2 threshold activation functions. This one has a threshold of T1. This is T2. And I'm just going to sum their 2 outputs at weight 1 and -1. Let's assume that T1 is lesser than T2. What happens as X increases? As X keeps increasing, until it arrives at T1, the output, both neurons are going to output as 0. So that overall output is 0. When X crosses T1, this neuron fires, but this neuron doesn't fire. So now when you sum these 2, the output is going to be a 1. And so the overall output when X is greater than T1 but less than T2 is 1. When X exceeds T2, the second neuron will also fire, and these 2 guys will cancel each other. And then the output goes back to being 0. So this little network, outputs are 1 between T1 and T2 and 0 otherwise. It gives you this little square pulse. And you can specify any T1 and T2. Once I do that, guess what? Let's say I want to model this blue function. I can just sort of segment this axis up into many little sections like so. I can have one subnet for each of these sections. I can scale their outputs by the height of the function within that region. And I have a network which begins to approximate this function. I can make this approximation arbitrarily precise by shrinking the width of these little boxes. And so this means that an MLP can model any arbitrary function. It can approximate any arbitrary continuous function to arbitrary precision over an input. You give me a tolerance to the error you can make, and I can construct an MLP that models it within that tolerance. And so here's my last poll. I'm kind of running out of time a bit, so I will stop this poll right now because I'm running out of time. But those of you who said none of the above, can someone explain why you said none of the above? Anyone? The correct answer is none of the above. You need only one perceptron, because if the activation function is sinusoidal, the activation function is y equals sine of z, then I can just say z equals 2x plus pi over 2. And so the bias is pi over 2, the weight is 2, and sine of 2x plus pi over 2 is cos of 2x. So you just need one neuron, right? Perfect. So you get the idea, right? And so here's where we are. We've sort of gone through all of these. We've added to our bullet list of things, interesting things an MLP can do. MLPs can also model continuous valued functions. And they can do a whole lot of other things. If you introduce loops, they can model memory. This was a very brilliant paper by Lawrence Kuby back in 1930. And it's the basis of a lot of architectures these days. They can represent probability distributions over integer real valued and complex valued domains. They can model a posteriori and a priori distributions of data. They can generate data from complicated or even unknown distributions. Your LLMs, right? And I just like to be facetious. I didn't know that there was a competition for people, rubbing their stomachs and patting their heads and standing on, balancing themselves. But apparently there's one. And what would you know? The winner is usually an Indian. Anyway. So here's where we are. Neural networks are functions. They take in inputs and compute outputs. Given an input, it computes the function layer-wise to predict the output. So more generally, given one or more inputs, it predicts one or more outputs. These AI tasks, each of these AI tasks takes in an input and produces an output. What's a box that takes in an input and produces an output? It is a function, right? These are all functions, and these functions can be approximated using neural networks. You give me a task, that task is actually a function. I know neural networks can approximate any function, which is why neural networks can do pretty much anything. And so, to end, interesting AI tasks are functions that can be modeled by neural networks, because neural networks are universal functions. They're universal Boolean functions, universal classification functions, and universal continuous valued functions. And so here's what we covered today. We went through a brief history, looked at connectionism and some early models and their limitations. We introduced modern neural networks, the multi-layer perceptron, and what they can compute. So in the next class, we'll talk about more on neural networks as universal approximators and the issue of depth. So thank you, folks. I think I ended bang on time, but I will stay behind for some questions.